What we have learned in the previous lecture is that for the Schrodinger equation solutions, we have integration psi m star psi n dx equals delta m n. So, we are assuming we have normalized the wave functions and summation n psi n star x psi n x prime equals delta x minus x prime. And we are going to use these two properties to show the equivalence of Heisenberg's and Schrodinger's approach, and then see how to connect the two. So, remember, the main thing in Heisenberg's approach is quantum condition, which says that P x minus x p is equal to h cross over I, which is h over 2 pi I. In matrix form, this means that P m L x L n minus x m L P L n, that means I am taking the m n component of this matrix P x minus x p is summed over L is equal to h cross over I delta m n. Can we get the same condition from Schrodinger picture? And what does it mean to have it coming from there? So, let us see that. So, to get this, first recognize step 1, that if I take this operation d by dx times x f, some function f, minus x d by dx f, this is equal to f alone. So, how do we see that? From the first term we get x df by dx plus f, and second term is minus x df by dx, and the first term and the last term cancel and you get f. Therefore, I can write that d by dx x operating on a function, by that I mean d by dx will act on first on x and then f both. This operating on a function means I will multiply x and f and then take the derivative. Minus x d by dx is like multiplying by 1. In particular, if I take f to be the nth eigenfunction of the solution of the Schrodinger equation, I am going to have d by dx of x psi n minus x d psi n by dx is equal to psi n. Let me now multiply both sides by h cross over I and write h cross over I d by dx x psi n minus x h cross over I d by dx operating on psi is equal to h cross over I psi n. Next, let me multiply both sides by psi m star x and integrate over x. So that I am going to get on the left hand side, I am going to get integration minus infinity to infinity dx psi m star h cross over I d by dx operating on x psi n x minus psi m star integration dx x h cross over I d psi n x dx is equal to h cross over I delta mn. This we have seen in the previous lecture that psi m actually orthogonal. So, orthogonality here is important. Now, I am going to use something else, and that is the completeness. So, what I am going to do now, write this as minus infinity to infinity, there is an integration over dx. I have psi m star x, I have h cross over I d by dx. I am going to write the inner integral, inner portion as minus infinity to infinity delta x minus x prime dx prime x prime psi n x prime, because of the delta function is nothing but x psi n x. But I am doing it so that I can write delta x minus x prime using completeness in terms of size again. And second term is therefore going to be similarly minus integral minus infinity to infinity dx psi m star x integration minus infinity to infinity delta x minus x prime dx prime h cross over I d by dx prime of psi n x prime. I am only writing this left hand side. So, this is my left hand side. Again, because this term in the second integral, because of the delta function, is nothing but h cross over I d by dx of psi n x. All right. So, this is what we have done. Now, I am going to use completeness. So, let me write this left hand side again, so that we can complete the whole thing right here. I have integration dx psi m star h cross over I d by dx integration of delta x minus x prime dx prime x prime psi n x prime minus integration dx psi m star x integration, this is all minus infinity to infinity, minus infinity to infinity, minus infinity to infinity, minus infinity to infinity delta x minus x prime dx prime h cross over I d by dx prime psi n x prime. That is my left hand side. And now, use completeness to write delta of x minus x prime as summation psi n x psi n star x prime. I am going to substitute this for delta function, so that the left hand side now becomes integration minus infinity to infinity dx psi m star. Let me be very careful, write this variable inside is x h cross over I d by dx of integration minus infinity to infinity, there is a summation over, let me change the index because I am using m and n. So, I am going to write this as n psi l x. So, I can write psi l x outside, because inside the integration it does not really matter, and then I am going to write psi l star x prime psi n x prime. That is the first term. For the second term, I am going to write again summation over L minus infinity to infinity dx psi m star x x integration minus infinity to infinity dx prime. I am going to put the x prime index inside. So, psi L x prime star h cross over I d by dx prime psi n star psi n x prime, and out here I get psi L x. Let me now put some brackets so that terms are easy to identify. I will put one bracket here, second bracket in the second term, one bracket here, and second one for the second integral. This first term is like a matrix element with m and n L indices. This term is also a matrix element with L and n indices. This is a matrix element with m L indices. This is a matrix element with L and n indices. I have summation over L, and I will put this whole thing in a big bracket, and I have the first integral minus infinity to infinity dx psi m star h cross over I d psi L x over dx. Second one is integration minus infinity to infinity dx primes, but since it is a dummy variable, I can still write this as dx psi L star x x psi n x minus infinity to infinity dx psi m star x x psi L x and integration minus infinity to infinity dx psi L star x h cross over I d by dx of psi n x big bracket. And recall, all this is equal to h cross over I delta m n. Now, let me assert, if we identify x m L as integration psi m star x x psi L x dx and P m L as minus infinity to infinity psi m star x h cross over I d by dx of psi L x dx. We identify it like this. What does this reduce to? It reduces to the summation over L. Inside the bracket I have P m L, second term is x L n minus I get x m L P L n is equal to h cross over I delta m n, and this is matrix mechanics quantum condition. So, if you want to have the two formalism equivalent, then there is a particular way of defining the matrix elements of Heisenberg's approach to quantum mechanics using the wave function in a very particular way, and that way is now called through operators. So, to have equivalence of Heisenberg's and Schrodinger's theory, P mn and x mn are defined from the wave functions using multiplicative, that is for x, or differential for p operators. So, I am introducing a term called operator. These are known as operators. So, for p ml, and is this equal to integration psi m star, then I apply p operator, sometimes it is written with a hat on top, psi l dx, where p operator is equal to h cross over I d by dx. For x ml, x ml I have psi m star x operator, I put a hat psi l dx, where x operator is nothing but just x and multiply by that. What about p square and x square? So, let us now check. What about x square? Remember, in Heisenberg's mechanics, x square mn would be equal to x ml x ln summation over L, which would be same as summation over L integration psi star m x x psi L x dx multiplied by integration psi L star, let me write this as x prime psi n x dx. And again, using completeness, I can write this as integration psi m star x times x dx. I will use summation over L psi L x psi L star x prime, then there is an x prime psi n, this is an x prime dx prime. This is nothing but delta x minus x prime, this is delta x minus x prime. So, this becomes integration psi m star x square psi n dx. So, operator for x square is x square. So, if we wish to calculate x square mn, this is going to be nothing but square of psi m star x x square psi n x dx. Let us see what about p square. P square mn is going to be integration minus infinity to infinity psi m star x h cross over I d by dx on psi n or L x times minus infinity to infinity psi L star x prime h cross over I d psi m by dx prime, this is all prime dx prime summed over L, because the first term is nothing but this is p ml and this is nothing but p ln. So, by the rule of matrix multiplication, this is what it is, and this again I can write as minus infinity to infinity psi m star x h cross over I d by dx operating on summation over L psi L x psi L star x prime. I can write it like this because d by dx does not act on x prime. There is an integration over x, and then I have h cross over I d psi n x prime over dx dx prime. But again, this term is delta x minus x prime, and therefore, this whole thing becomes minus infinity to infinity psi m star x h cross square d2 psi by d x square dx. So, for p square mn, I did p ml p ln summed over L, and this I wrote as integration psi m star h cross over I d psi L over dx x, and this is minus infinity to infinity psi L x prime star h cross over I d psi n over dx prime, this is all prime dx prime. Then I use the orthogonality condition to show that this is equal to psi m star x minus h cross square d2 by dx square psi n x dx integration. This therefore is the operator for p square, and you can see that p square operator is nothing but p times p operator. So, if I want to calculate p square, I do not really have to go through the matrix route. I can straight away write this is equal to psi star m x p square operator, which is minus h cross square d2 by dx square psi n x dx. So, you see how things become very easy. I do not really have to do matrix multiplication all the time, and I can perform these operations. I can make operators for anything. They just multiply the operators and you get the answer. So, this now makes a equivalence of the Heisenberg picture with Schrodinger picture, where now from the wave function I extract the matrix elements by applying the corresponding operators. Does it make sense? Let us see that. So, the question now I have question. Does it make sense? In particular, for x, one is multiplying psi by x. So, there it seems to be okay that if I want to calculate x, I just multiply by x. It will be clearer in the next lecture when I give the Born interpretation for the wave function. But differential operator? H cross over I d by dx giving momentum, that looks a little odd, but let us see does it make sense. Recall, for a particle moving with momentum p, the wavelength is h over p, k which is 2 pi over lambda is 2 pi over h p, which is p over h cross, and the static part of the wave function is e raised to I k x psi x. It is a plane wave for a fixed momentum, and let us now apply p operator on psi x, and let us see what does it give. So, when I do p operator psi x, it gives me h cross over I d by dx operating on e raised to I k x, and that gives me h cross k e raised to I k x. So, in this case, when the particle has a pure momentum p, applying p operator on psi gives me that momentum. So, it does make sense that p operator gives me momentum. That means, this is an operator that extracts, right, the momentum out of a wave function. So, in a very loose statement, I will just write this: p operator extracts the momentum from a wave function. And that is the formalism in Schrodinger, that whenever you want to extract a quantity, it has to have a corresponding operator that then acts on the wave function and gives you that quantity. Incidentally, here, since you get exact momentum, so this is a momentum eigenstate with the eigen value of the operator being h cross k. Let us look at it slightly differently. What about the energy? The Schrodinger equation is minus h cross over 2 m d2 by dx square operating on psi n plus Vx psi n is equal to E n psi n. What did we say this operator was? This is 1 over 2 m minus h cross square d2 by dx square psi n plus Vx. Now, Vx you can write as a polynomial or whatever, and we saw that that also is like an operator operating on psi n is equal to E n psi n. In operator language, this will become, this is p square. So, it will become p square operator divided by 2 m plus V operator, which is a multiplicative operator, acting on psi n gives me E n psi n. And what is this? P square over 2 m plus Vx, it is like an operator for the energy. So, operator for the energy acting on the wave function gives me the energy. So, this suddenly starts making sense, that P operator being written as h cross over I d by dx, in two instances it has given me the right answer. For e raised to I k x, P acting on e raised to I k x gave me the true momentum P times e raised to I k x, and for psi n x, P square over 2 m plus V x on psi n gave me the energy. So, this operator for the energy is known as the Hamiltonian. And in this course, this is an introductory course, so I am not going to go more into the details of why this is called Hamiltonian, but this is the Hamiltonian operator. So, Hamiltonian is the operator for energy, it acts on psi n, an eigenfunction, and gives you E n. So, to conclude this lecture, let me just make a comparative table for Heisenberg and Schrodinger picture. So, I will conclude this lecture by making a table of Heisenberg, Schrodinger. In Heisenberg's picture, the x and p are represented by matrices. In the Schrodinger picture, particle has a wave associated with it, which is known as the wave function, x alpha beta or xmn and p alpha beta are extracted, or I will use constructed from psi using operators. So, there are matrices, and here you have to apply an operator on this function. Now, here the equation of motion is classical, except that now this is written in terms of the matrices. Here is the wave equation. Here the quantum condition is Px minus xp equals h cross over I, the identity matrix. Again here I will write wave equation and P mn equals psi m star h cross over I d by dx psi n dx, x mn being given as psi m star x psi n dx. Here the energy for stationary systems or conservative systems is diagonal matrix, and you have done that in the past for harmonic oscillator. Here the energy is eigenvalue of Schrodinger equation. However, through all this, finally the energy for harmonic oscillator, right, SHM, comes out to be n plus a half h cross omega, and here also we have solved this. Energy for SHM comes out to be n plus a half h cross omega, and the two are equivalent. So, after this conclusion, I just want to leave you with a question: what about diagonal terms? For example, x n n, which is integration psi n star x x psi n x dx, which is integration mod psi n x square x dx, and p n n, which is integration psi n star x h cross over I d psi n over dx dx. These terms we have not yet addressed. What do they mean? And we will address this in the next lecture when we discuss the interpretation of psi n square. So, I leave you with that question in this lecture.